Good afternoon. In the previous first lecture, we talked about the objectives and the scope of this course. So let's continue review what we talked about. We said that the objective is to learn how to analyze the dynamic behavior of a structure. And the word dynamic means time variant. So we have a time variant force, such as the wind speed or the force on the wheels of a car because of the rough road. And we want to find the response. And there are several steps in this process. The first one, as we see here, is to start with the structure or a system that is the real system. Now, this may already exist and you want to analyze it, or you may have some drawings and you may have defined that system you want to analyze it. So you start with this system, the real system. Now, as we said, you cannot do a complete analysis of that system because this is really, really complicated. So we do some assumptions. We simplify this into something much simpler, such as this collection of bars and rods, and concentrated masses. Then you write an equation of motion, and then you solve this equation. And you do that typically on the computer. And we said that the most complex and not really complex but challenging task is to go from something that is real into a model, a simplified model. There's no structured approach for that. You have to rely a lot on experience and intuition. So a system is a combination of components that act together, and the objective is to learn how to model structural systems and solve the models to predict the behavior. So modeling is one part, and then once you have the mathematical model, then solve it to find the dynamic behavior. We classify different systems in a different way, and we said that systems are either linear or non-linear. Systems also can be classified into time variant and time invariant. A time invariant system is a system, as the word says, that the properties don't change with time. In a time variant systems, the properties do change with time. We can also classify systems in a different way. Single degree of freedom systems, where you need one variable to represent the system, to specify the position of the system. Multi-degree of freedom system, where you want multiple variables, and continuous systems, where you consider the system as is with an infinite number of variables that you need to specify its position. And we said that in this class, we're going to focus on linear systems. The systems will be time invariant. We'll not see systems that change with time as they vibrate. And we'll consider all the three types: single degree, multi-degree, and continuous systems. And in terms of the sketch, the scope of the course is described by, or corresponds to these three bullets. So, time invariant, linear systems with single degree of freedom, multiple degrees of freedom, or continuous systems. Then we talked about the definition of a linear system. A linear system is described by an equation that it is linear in terms of the unknown quantity. There are no quantities, but it counts, and you have only first powers of this quantity or the derivatives. So no x squared, no product of x times x dot, or no nonlinear function like, say, cosine of x of t or sine x of t. If you had a sine or cosine of x of t, the system would be nonlinear. An important property of a system that is linear is that if you apply two forces simultaneously to the system, the response will be the sum of the responses to the individual forces. This is called the superposition principle. If you double the input, the force, the response will be doubled. Okay? A system can be visualized as a box with one function that drives or excites the system and the response to the system. Okay? So if the system is linear, if you double the sign, so will do the response, x of t. A nonlinear system has a differential equation that has nonlinear terms in terms of the unknowns. So here is a nonlinear system. The displacement, you have the cubic function of the displacement. This is nonlinear. Superposition principle does not hold, which means, well, if you have an input sine of t plus cosine of t, and you have already the solutions when the input is sine, and when it's cosine, then you cannot add the two solutions. You have to solve the differential equation when the input is sine of t plus cosine of t again. Okay? So dealing with nonlinear systems is more challenging. A time invariant system is a system whose parameters don't change with time. Okay? A time variant system is a system whose parameters do change with time. This is a time variant system because the coefficients of the unknown x of t changes with time because of this cosine. Okay. We also classify excitations. We have static excitation that doesn't change with time. For example, the weight of something is constant. So if this is the only force that is exerted, this is a static system. This is static excitation. Dynamic means something that changes with time. So if the force changes with time, you have a dynamic problem, dynamic excitation. Now, the excitation can be deterministic, which means you know it. You can write an equation about excitation, or you can draw it, and random, well, you don't know that. In this class, we're going to focus, as we said, on deterministic systems with dynamic excitations. So we'll focus on this problem. If you take a class with statics class, then you'll work with this. If you take a class on probabilistics, and then you'll be here. You'll deal with this too. Okay. So this was the introduction, and what we're going to cover today is the new material is equations of motion, how to derive equations of motion of systems with 1 degree of freedom. principle, degree of freedom systems. In the book by Roy Craig, this is chapter 2. And we work with the derivation of the equations of motion first. That means that we have a conceptual model, something with masses, springs, dampers, and we want to write the equation that relates the force to the displacement. And we'll talk about three methods. The first one is called the unit displacement method. The second one is Newton's law. And the third is energy principles. Okay, today we'll deal with the first two. Okay, so let's talk about a general strategy. Okay, the first step, and this applies to both methods A and B, what is the first step? The first step is to define first the degree of freedom. Now, if you have one degree of freedom, it may be obvious what you should use, but it may not. It might be that there are two or more choices of degree of freedom. And although if you use the method correctly, you will find the correct equation with any choice, sometimes the choice can make your life easy or difficult. So the first step is define the degree of freedom or independent coordinate. Define the independent coordinate. This is called also degree of freedom. Or if you have many degrees of freedom, degrees of freedom. You consider the forces that are applied and the moments. So consider all applied forces and moments. And the third step is apply Newton's law. Okay, so this is the strategy that you will follow. First, you select a degree of freedom, something that defines the position of the system. Then you draw all the applied forces and moments, and then you use Newton's law. Now, if we deal with dynamics, that means forces and displacements that change with time, we do not consider static forces, okay? So in order to do that, you write the equations with respect to the static equilibrium position, okay? So write equations the static equilibrium. So consider only dynamic forces and moments. Okay, when you consider the static equilibrium position and you measure everything relative to static equilibrium position, static forces are not important. And the reason is because for every force there is an equal and opposite force that cancels the first one. So because they are cancelled, they are coming to pairs that cancel each other, you don't need to consider them. For example, if you have a mass that is suspended by a spring, okay? The mass is M and the spring stiffness is K. There is a weight because of the mass, okay? So, should we consider it? Well, let's draw it. There is a weight mg. Now, if this position is the static equilibrium position, then there is an equal and opposite force because of the deflection of the spring. So if this is the static equilibrium, you have at the same time a force because of the static deflection of the spring. So there is a force because of the static deflection. And the two forces are equal and opposite. So they cancel each other, so you don't need to consider these forces. Okay? So we'll only consider forces that are dynamic. Okay? Now, sometimes a force that is static generates a moment that is dynamic. What is an example? Well, consider a pendulum. This is a pendulum here. This is the supporting point, and there is a weight here. Okay? There is a force F because of the weight. That is a static force, but you have to consider it. Why? Because it generates a moment which is dynamic. As the pendulum swings back and forth, you have a moment about this point, a moment which is time variant. So you have this moment m of t, which is equal to the force of the weight, so it is F times this distance here, which changes with time. So this can be let's say, y of t. So this is dynamic. So the moment is dynamic, so you have to consider this. Okay? So if a force does not induce a dynamic moment, and it's static, then you can neglect it. Otherwise, if it induces a moment that changes with time, you have to consider it. Okay. There are three types of forces. One is the inertia force, the other is because of damping, and the other is because of springs, spring forces. So types of forces. Inertia. And inertia force is because of mass or maybe a moment of inertia. This is proportional to the acceleration. So you will see a term in your equation of motion that is proportional to the acceleration. So proportional to acceleration. And this is m, an example, m, x double dot, okay? So you have one term, or a group of terms, if you have multi-degree of freedom systems, for which forces are proportional to acceleration. Then you have damping. Damping forces are proportional to the velocity. Proportional to velocity. And then you have spring forces. And these are proportional to the displacement. Kx. Okay. So let's talk about the unit displacement method that considers or finds these three types of forces in step by step. Okay. So instead of writing directly the equation of motion, finds these terms and then puts them together into one equation. So, unit displacement method. The first step is to define the degree of freedom or independent coordinate. Which is either x or theta, either a displacement or an angle of rotation. Now, the next step is you consider that you create a displacement to displace, say, this mass very, very slowly, so that the velocity and the acceleration are both zero. And then you find the force that is required to produce this result. That means to displace this mass by some amount x. So, assume displacement x. Or an angle of rotation theta, depending on the problem. Keep the velocity and the acceleration equal to zero. Or if you deal with rotations, the angular velocity and the angular acceleration equal to zero. Okay? And then you find the force in case of the displacement, or the torque or moment, if you deal with rotations, to produce this result. So find Fk or Mk moment necessary to produce this result. Okay, so once you find this force, if you divide it by the displacement that corresponds to the force, that will give you the equivalent stiffness. So, put K equivalent equal to the force that is required to induce displacement x divided by x. Or if you work with rotation, then K equivalent is equal to the moment divided by the angle of rotation. So that gives you the first term that has to do with displacements, okay? So it gives you this part of the equation. Okay, now if you want to find the term that has to do with damping, then you assume a velocity x dot linear or an angular velocity theta dot. And you keep the other two quantities zero. So you keep the displacement and the acceleration zero, or the rotation and the angular acceleration equal to zero. And you find either the force Fc or the moment mc necessary to produce this result. And then you define the terms that they have to do with velocity or acceleration, so the damping terms. So equivalent damping is Fc over the velocity, or if you deal with rotations, the moment mc divided by the angular velocity. Okay, so this is for the terms that they have to do with damping. Now, for inertia, we do the same thing. So for assume some acceleration, linear or angular. You keep the displacement and the velocity zero, or theta and theta dot zero. You find Fm the forces and moments to produce this result, and then the equivalent mass is Fm divided by the acceleration and if you work with rotations, the equivalent moment is mx divided by x double dot. Okay. Now, once you have the three quantities, equivalent mass, equivalent damping, and equivalent stiffness, you can assemble the equation of motion. So you are ready to write the equation of motion. Equation of motion is M equivalent x double dot plus C equivalent x dot plus K equivalent times x equal to f of t. That's the equation of motion. Or if your degree of freedom is rotation, then you have equivalent moment of inertia times theta double dot plus C equivalent times theta dot plus K equivalent. But now this K equivalent is the stiffness of a rotational spring. So this is multiplied by theta, and this is the exciting moment. Okay, so that's the equation. So you divide the problem into three parts. First, you determine inertias, this term, damping, and then stiffness, the term that has to do with stiffness. Okay. Before we do examples, I like to talk about Newton's law. There are two versions or two groups. One is for translation, the other is for rotation. Let's start with translation. We consider three-dimensional space. X, Y, Z. Let's say that we have a body. This is a rigid body. The center of gravity is G. Okay. Then you have another reference point A, and consider that the acceleration is on the center of gravity. The acceleration is AG. This acceleration of the center of gravity, which is a vector. Okay? And we'll connect the center of gravity to another point that you may want to consider as a reference. And then suppose that you have a small element here in the body, and the vector that connects A with this point is rho. Okay, so the equation for translation is that the sum of all the forces is equal to the mass times the acceleration, and we're talking here about the acceleration of the center of gravity, okay? So this is a vector equation which corresponds to three equations, one in the x direction, the second is in the y, and the third in the z direction, okay? So this is the equation of Newton's law for translation. Okay. That's pretty simple. The important thing to remember is that you have to consider accelerations in their corresponding directions. So if you have a force in the x direction, then this, you have to consider the acceleration in the same direction x. Okay, now for rotation, things become more complicated. And the choice of the reference point about which you are going to write Newton's law is very important. So let's consider first as a reference point the arbitrary point A. Okay, then the moment about point A, actually you have three components of the moment, so it is a vector. You have the integral over the body of rho, okay? So rho is this vector. The cross product of that times the acceleration of A, and you take the integral over the entire mass. That's the first term. There is a second term, which is the integral rho cross product of the angular, the derivative, the time derivative of the angular velocity, cross product rho, dm. That's the second term, okay? And there is a third term, which is the integral over the mass of okay, so here we relate the moment with respect to the reference point A with the angular acceleration, okay? So this is the equation, Newton's law, and as you can see, it's pretty nasty. Now, let's see how we can choose the reference point strategically to make the equation simpler. Okay, first if you consider a plane motion, so instead of three-dimensional space, you have a plane motion. For translation, the sum of all the forces is equal to the mass times the acceleration of the center of gravity. Nothing changes. It's the same equation as before. Now for rotation, things are a little bit simpler. Now let's make a sketch. The center of gravity, G, and the reference point, which is different than the center of gravity, A, this is the line that connects them, and you have the horizontal component and the vertical component, so you have X bar and Y bar, okay? This is the acceleration of point G. A, G, okay? And for this point A, you have an acceleration A, and the two components are AX for the horizontal component and AY of the vertical component, okay? Now, the equation again for rotation, for Newton's law, becomes the summation of all the moments about A, the reference point, in the Z direction. We have three terms. We have the acceleration of A in the Y direction, this acceleration, times X bar, times the mass, minus AX times Y bar times M plus angular acceleration alpha times the moment of inertia of A, okay? And this will be on this plane, so it is Z, okay? So this is the law for rotation. Now, let's consider some special cases where this is simplified. What if the reference point first A coincides with G, the center of gravity? Okay? So two special cases. The first one is when the reference is the center of gravity. A coincides with the center of gravity. Okay? Newton's law for translation doesn't change. The summation of all the forces is equal to the mass times the acceleration of the center of gravity. That doesn't change. What changes, and it becomes simpler, is the law for the moments. So for rotation, what happens to the equation? Well, the sum of the moments about the center of gravity in the z direction, well, let's see this term. X bar and y bar become 0 now, because A is same as G. So the only thing that varies angular acceleration times the moment of inertia about G. Okay? So the equation becomes pretty simple. The summation of the moments is equal to the angular acceleration times the moment of inertia with respect to the center of gravity. Okay? So if you try to write the equations of motion with respect to the center of gravity, then this is good because it's a very easy equation to remember. The summation of all the moments is equal to the angular acceleration times the moment of inertia about the center of gravity. Okay, so this is one case. Now, another case is where A is pinned. That means it is a pivot point. The body can rotate about A, but doesn't move relative to A. What happens to the second equation? Okay? If it is pinned, then it means that these components, the acceleration in the x direction and in the x direction and the y direction, these are linear accelerations are 0. So again, the sum of the moments is equal to the angular acceleration times the moment of inertia about the reference point. Okay? So in this special case, you don't have linear acceleration of that reference point. So the summation of the moments with respect to the reference point which is pinned is A times the moment of inertia about that reference point. Okay, so one recommendation, if you want to make your life easy, is to choose as the reference point about which you will write the equation of motion either the center of gravity, or alternatively, if there's a pinpoint, consider this as the reference. And then it will be easier to write the equations of for Newton's law in terms of rotation. So recommendation, consider as a reference point the center of gravity. If there is a pinpoint, then consider that pinpoint as the reference point. If that is a pinpoint, consider it reference as a reference. Okay, so if you have a wheel of a car and you are writing equations of motion, it's advantageous to write equations about the center of the wheel. Okay, center of the wheel, which is the center of gravity. Okay. So we'll start doing an example, and we may have to continue in the next class session if there's not enough time to finish it. We have this system. A spring is connected to the wall. We have a mass M, and we call this point C. We have a damper. So let's say this is capital C, to distinguish from the damper. And then you have a rod that is massless, and the rod is pivoted about this point, A. There is a mass at the bottom, 2m, and we call this point B the center of the mass, point B. This distance is A. This distance is B. And you have a force, F of t, a dynamic force, okay? So this is a pivot point here, and the rod will oscillate back and forth, okay? And because of this force. And you want to find the equation of motion. Okay? We assume small displacements and rotations. So, assume small displacements and rotations. Okay. How many degrees of freedom do we have? 1. Because if someone determines the angle of rotation of the bar, and the bar is considered rigid, then you define the position of the system, okay? So there is 1 degree of freedom system. This is a 1 degree of freedom system. And there are 2 options for, actually there are more than 2 options for the degree of freedom. One would consider the angle of rotation. So theta could be 1 degree of freedom, okay? That's one choice. Someone may want to consider as a degree of freedom the displacement of the lower mass. And since the rotations are small, this is a horizontal displacement. So someone could consider the displacement of the lower mass. Or an alternative could be to consider the displacement of the upper mass. So there are three options, and let's choose the option, the second option, where the displacement of the lower mass is a degree of freedom. Okay? So there is 1 degree of freedom. Although there are different options, there is one independent degree of freedom. So 1 degree of freedom. And this is x of t, the displacement of the lower mass. Okay? So this is x of t. That's the degree of freedom. And this is the horizontal displacement, okay? Now, if we want to work with the terms that have to do with the displacement, we'll consider a displacement x and find what is the force that is needed to produce this displacement. So let's make a sketch here with all the forces if we displace the lower part by x. Okay. So the reference, the horizontal, at the vertical position, I'm sorry, this is the vertical position of the beam. This is the point A, the pivot. Okay. And now you have some rotation. Okay. The lower part has been displaced by x. Okay. This is B. This length is A. The upper part, the displacement is x times A over B. Okay? This is the horizontal motion of the upper part. Okay? Now, this distance is, you can write it as square root of b squared minus x squared from Pythagorean theorem, which is equal to b times square root 1 minus x over b squared. Okay? So this is the vertical distance from A, the pivot, up to this point. Okay. If you want to write this distance is A times square root 1 minus x squared over b squared. Okay. Now, let's put the forces that are exerted on this bar when it's displaced to this position very, very slowly. So there are no inertia forces. You only have forces because of the weights and, yeah, actually, the only forces are because of the weights, but also the force F of t. So let's put first the force F of t. It is here, F of t. You also have the weight, okay, which is 2 times mg. Well, the weight is a static force. But as we said, we got to be careful, since this length of the arm changes with time. This is a time-varying moment. It induces a time-varying moment, so it has to be considered. Okay? On the upper part, you have mg, the weight of the upper part, and that actually tries to disturb the system away from the equilibrium. And then you have the force because of the contraction of the spring. When the mass moves to the left, it squeezes the spring. So there is a reaction because of the spring, and this is the stiffness of the spring, K, times the displacement, which is x A over B. Okay? X A over B. Okay. So now we'll write the equation that relates the equation of equilibrium. That means the summation of all the moments, there are 4 moments because of these forces, the summation of all these moments is equal to 0, right? Okay? So let's write this equation. Summation of all the moments about A is 0. Okay? So we have Fk, the spring, force Fk, times B, times square root of 1 minus x over B squared. Okay. Then we have the moment because of the weight, which is mg xa over b minus 2 times mg x minus kx a squared over b square root 1 minus x squared over b squared equal to 0. Okay. So Fk is the force that is needed to displace the lower part by a unit amount, okay? Now, if we linearize these 2 terms that are in the square root, the square root 1 minus x over b squared is equal to 1 minus 1/2 x squared over b squared, this is Taylor expansion, plus higher order terms, and assuming that x is small, x squared becomes negligible. So this can be assumed to be equal to 1. So this thing that is in the square root can be assumed to be equal to 1, and so can be this part. Okay? So if you do that, and you make this 2 equal to 1, you can calculate f of k. F of k will be k times a squared over b squared plus 2 times mg divided by b minus mg a over b squared times x. Okay? So the force that it is required to produce a displacement equal to x at this point is this quantity, which is a constant, times the displacement. Okay? So what is the equivalent stiffness? What is K equivalent? Okay? That means what is the force that is required to move the lower part by 1 unit? Well, it's this coefficient. So the K equivalent, that means the spring that is equivalent to this system, is simply the quantity in this parenthesis. So K equivalent is f of k divided by the displacement x, and this is equal to k times a squared over b squared plus 2 times mg over b minus m, I'm sorry, let's make it clearer, mg times a divided by b squared. So this is K equivalent. So if you wanted to represent this whole system by just one point, that you have a mass, a stiffness, and a damper, well, the spring that would connect this point to the wall would be equal to this value K equivalent. Okay? So this is the first part of the equation. Next time we're going to complete the equation, which will be M equivalent times x dot plus C equivalent times x dot plus K equivalent times x. So far we have found K equivalent. Okay? So next time we'll complete this equation by finding the other terms. Oh, I'm sorry, and if you have an external force f of t as we assumed, this is f of t. Okay, so today we talked about 1 degree of freedom systems. We said that there are 3 methods that you can derive the equations of motion. The 2 actually are pretty similar. The unit displacement method, where you consider unit displacement and you find the force that is required to produce this result. The second one is just Newton's law. And the third one involves energy principles. Okay, let's stop here.